I want to introduce today's keynote speaker, who's also going to lead into our panel. Chris Holmes from Planet, who's a fellow in Open VP Product Strategy. Chris does everything. I've known Chris for many years. Chris, of course, was one of the leaders in founding this community. He was the head of OpenGeo, and then at Boundless, then at Planet. Chris has been extremely important in launching many technologies, GeoServer, GeoNode, and now all his work on the Queriable Earth. So I'm going to turn it over to Chris and let him take it away with our opening keynote.
Thank you, Eddie. Wait for my slides to get up. So I'm Chris Holmes with Planet. Psyched to talk here. I see something. You do not. There we go. So I'm going to dive right into it. The last FOSS4G talk I gave was 5 years ago, describing a vision for Queriable Earth and a number of these foundational standards and technology to get there. The core idea is simple. We should be able to ask questions like, how many roads in China were built in the last year? Or how much deforestation has there been in the state of Pará in the last month or the last day? And send me a notification so I can do something about it. The query interface for Queriable Earth is now far clearer than it was 5 years ago. You should be able to just use a chat interface and have it answer questions about the state of the planet like ChatGPT does for literally every other type of data. In that talk, I laid out a bit of a roadmap to get to Queriable Earth. And I think we as a community have actually done pretty well on many of the foundational geospatial pieces. Many of these were quite new or even speculative at the time. COGS and stack are now much more common. I just found out about geoplatform.gov. It's awesome to see the federal government embracing stack. There's been a lot of advances in analysis-ready data, making for much nicer images, but more importantly, fully harmonized pixels to support analysis. There's advances in processing engines, Earth Engine, Sentinel Hub, plus open source platforms like Dask and Sedona, which have Earth Mover and Where Robots, respectively, as new startups behind them. I do think the last three have been a bit slower than I was expecting. I had hoped we'd see a more centralized commons and a raft of truly open and useful computer vision models. But progress on each feels like it's been accelerated recently. So it seems like we made good progress on that roadmap, and the query side of Queriable Earth is pretty much completely solved with the explosion of LLMs. But I think there's a key thing we need to figure out on the geospatial side to meet that potential. So Planet and Microsoft put this demo together. This is not playing. Anyways, oh, there it goes. Using Planet's land surface temperature and forced planetary variables. It's pretty compelling, but it's far from complete Queriable Earth, as there's only 2 or 3 types of questions you can answer, and it's only in California. Our goal is not a queryable California forest carbon, so it's not enough to have a model that just detects roads or gets forests. We need hundreds of pre-processed global data sets, canopy cover, tree species, fields and yields, water quality, buildings, ships, solar farms, plains, pastures, many more, so users can query any spatial area that they want, not just pre-canned areas. And it needs to have full historical data, as most questions involve change and not simply the current state. There's obviously huge potential to use the latest AI and all the satellite imagery coming down, and I could probably fill a whole talk about the latest advances in this, but that's not what I really want to talk about. What I want to talk about is now a pretty old concept, the spatial data infrastructure. There's lots of definitions, but let's pick one. SDI is a coordinated series of agreements on technology standards, institutional arrangements, and policies that enable the discovery and use of geospatial information by users and for purposes other than those it was created for. In the US, we have the national SDI, and the goals are in line. Let's make lots of geospatial data available and easily integrated to enhance the understanding of our world. But I think we need to be honest with ourselves that SDIs have missed their moment. I believe if there's lots of truly valuable geospatial information truly available and accessible, LLMs would be slurping it up with ease and letting people query it. Instead, all geospatial knowledge in AIs is based on what was written online and usually falls short for questions that are easy if you have the spatial data. To me, the core problem is we've continued to let spatial data infrastructure be this abstract task, not something to be solved with real urgency. This quote kind of haunts me. I remember reading it in the mid-2000s as I was working on open source software for SDI implementations. And the concept had been around a while, and this explanation just seemed to me to justify a lack of success. It's just going to take decades. But I feel a real urgency. The major problems that face our planet, climate change, biodiversity crisis, healthcare, peace and security, feeding everyone, are all spatial in nature. But spatial data is rarely used by those making the major decisions that impact everybody. I spent the first decade of my career working in GeoServer and OpenGeo, and from that experience, I've come to believe the problem is that the core architecture to implement the SDA concept has been too complicated. We definitely let the architecture astronauts take over, handing down unrealistic requirements from their imaginations instead of centering on practical problem of actually sharing data. I still believe the core vision's awesome. Like, everyone with spatial data should be able to share it interoperably so users can easily discover it, use it for diverse purposes, but we're clearly not there. SDI implementations are not easy to use, and they're even more challenging to publish to participate in as a data producer. So I know it's not all tech. Like, you can't just build some amazing software and everybody's gonna come, but you need the policies to ensure the sharing of information. But in this case, I actually think the policy people have done a pretty good job. Inspire was signed into law for all of Europe, requiring environmental spatial data to be shared openly. The Geospatial Data Act of 2018 in the US has set some great policy. But I think things went wrong. When Inspire law came down, the way for a small municipality with a half-time GIS person to publish their data was just unrealistic. To share a few layers of vector data, this GIS person would need to stand up a WMS, a WFS, a CSW, configure XML schema mappings, to do on-the-fly translation of their database into required GML profiles. So my radical thought is that the core problem of creating infrastructure to make geospatial data easier to find and use is something a motivated group of people can solve, and that the FOSS4G community will be at the center. The key, I believe, is to keep it incredibly simple. A number of us have been collaborating on a series of specifications, pushing each to be as simple as possible. It's time for a new type of SDI, the Cloud Native Spatial Data Infrastructure, or perhaps the Keep It Simple Stupid SDI. I don't think the ecosystem's completely ready for prime time, but I think there's a clear, accomplishable roadmap with the potential to make geospatial information vastly more relevant to major decisions about our future. At the heart are a series of standards that share commonalities and are collectively called Cloud Native Geospatial. I'm excited we now have a foundation pushing these efforts forward, as Radiant Earth has doubled down on their work here to make it one of their 2 major activities. There's little core work that remains on the standards, but tons of work to build out the ecosystem, create more extensions and common data schemas, and get all the data in one of these standards. I'm going to give a quick overview of the more mature ones. COG was old news, my talk 5 years ago, but it proved out this concept of streaming geospatial data on the cloud instead of passing it around. ZAR excels at multidimensional data. There's now petabytes of data available on weather and climate modeling. Copic's a bit newer, uses the exact same COG playbook. Take an established format and organize it better for the cloud. And stacks our metadata. Works across all the formats, lets you take a slug of JSON, put it next to any file to communicate about what's in that file. So that's the core, but I want to spend a bit of time diving deep into the latest advances that have emerged. I have a strong hunch they're going to complete our suite of standards. The first is PM tiles. A couple years ago, there was a number of different takes on Cloud Native MB tiles, the Mapbox SQLite format. One of those was PM tiles, but by version 3, it was head and shoulders above the rest, bringing a fast, compact format that handles raster and vector data. It lets you take a single file, it's optimized for serving tiles, and that lives on the cloud. You can have a 192 gigabyte file of every building in the world that's directly accessed by clients, no server at all. This is an awesome data set combining open building footprint detections from Google and Microsoft. PM tiles enables instant visualization, which to me is really key. You need to get a sense of the data. You need to start streaming it and see it. And then it can be served up as traditional WMTS or XYZ tiles by a bit of code in between. Vita, the company behind the combined buildings data set, in turn uses PM tiles hosted on Source Cooperative in their own climate risk scoring application, but styling it to fit into their UI and cartography. The cool thing is that anyone can style the data as they want. This example is Felt, one of my favorite new tools, connecting to the same PM tiles, but you can make use of all of their nice styling options available and then share that map with others. Those people in turn can style it as they want, add additional layers, and tell their own story. The architecture is much simpler than past efforts where the client would pass a complicated style layer descriptor, XML, to a server to do the rendering. With PM tiles, the vectors are directly streamed to the user and rendered in the browser with incredible responsiveness. The data provider makes choices about generalization, but the user gets full control over the styling. I think this starts to demonstrate the potential of the Cloud Native SDI, where advanced tools don't need to connect to a server. They can just use the data directly, streaming and styling it on the fly. You can also use PM tiles to filter through huge amounts of image footprints, essentially doing search like you would with an API, but not having to wait for any server responses. This is a couple million SkySat footprints, and you can filter by date, clear percent, view angle with instant responses. And you can even view the cog or the web tiles, take it to another application like Felt. This is still very much a prototype, but I believe it demonstrates the potential to build powerful applications from simple cloud native primitives. The other new standard I want to dive into is GeoParquet. It's a very simple standard, just defining geospatial columns on top of Parquet, which is widely used in the data science and data engineering worlds. The result is consistently smaller and faster than other geospatial formats, which is a great core attribute to sort of rest on. And it's quickly getting adopted by a wide ecosystem. We just went to 1.0 a couple months ago, and there's already 20 different tools and libraries and a lot of data available in the format. It's also emerging as a performant format for the web, with this demo rendering 3.2 million points and first-class support in DecGLs coming soon. Another powerful aspect is Parquet's ability to partition huge data sets. Lately, I've been translating a couple global building data sets from Google and Overture into GeoParquet. I ended up down this kind of deep rabbit hole of a side project, learning about Parquet partitions and trying to make them work for geospatial. What I really wanted was a way to distribute data that's intuitive for a kind of traditional geospatial workflow, where you navigate to a folder, find the country or state file that you want, download it, and start using it. To be clear, I love this workflow and use it all the time. I built WFS support into GeoServer, and I still don't think I've connected to more than a handful of WFS servers, but I download geospatial data and load it into QGIS all the time. The only problem is you've got to wait for the data to download. Even if I just care about a small town in Uganda, I still have to wait for the full country to download. My connection's pretty fast, and it's still 9 minutes awaiting, not doing the task I wanted to accomplish. And slower internet speeds, it'll be much longer. But ideally, you could query the entire data set in a cloud native way. This is a little command line tool I wrote that's powered by DuckDB. Lets you take an arbitrary GeoJSON file and translate and transform it into any common format. It takes 30 to 60 seconds to query and download. And if you hint which country it is, it's more like 5 to 15. There's a lot we could do to get the performance up, but it's pretty awesome I could get a request down to 10 seconds across this huge data set. I'm hoping somebody will code a QGIS plugin so you can request directly from there. And to be clear, there's no server in the mix at all. The engine that's powering the previous request is DuckDB on my laptop with this SQL query. It points at the entire 150 gigabyte set of Parquet data on the cloud, and then DuckDB queries the stats with HTTP range requests to make its queries very efficient. You can even run DuckDB in the browser, compiled as WebAssembly, which I think has a ton of potential. This is using the Places Overture data set and shows how you can use DuckDB to query in a cloud native way. The center of it is what I'm calling the admin partition GeoParquet distribution. Not the most creative name, but I think there's something really interesting here. You can distribute data in a folder structure that traditional workflows can use, while also making it available as a complete data set that you can query directly in a serverless manner. So 10 seconds is cool, but could we do even better? Continue to ride the innovations in the mainstream data world. There's tons of momentum on what are called table formats. These build on Parquet partitions, but further optimize the Parquet files, and then add a layer of JSON metadata, enabling even faster access across many Parquet files. It enables versions and schema evolution, effectively turning a set of Parquet files into a database. There's few efforts, but energy is coalescing around the Apache Iceberg format. And the coolest thing, there's new spatial table formats, with Havasu just announced today by Where Robots. This is a fork of Iceberg to add spatial capabilities, enabling even faster query times, full ACID compliance, and incredible spatial joins. And it's all GeoParquet under the hood. The exact same query that took 48 seconds with DuckDB can be done in under 3 seconds using the Havasu table format. You can then scale out processing with Havasu, analyze and join billions of rows and terabytes of data in minutes. This all operates directly against stack, cogs, and admin partition GeoParquet data. SidoniaDB lets you treat the growing cloud native infrastructure as a database, but without having to download or import anything. SidoniaDB is following this trend that's a big deal in the mainstream data world, the separation of query and storage. It's long been that the database was a single technology that stored the data and queried it. But in recent years, that relationship has been decoupling. You can see this even with DuckDB. I don't have to load the data into DuckDB. I can just treat GeoParquet files as the database, doing all the queries I want to. And this isn't a trend of just a few little startups. The big cloud data warehouses like BigQuery and Snowflake are supporting Iceberg, and lots of money is invested in this new architecture. So I think this has some profound implications for our spatial data infrastructure. It flips the traditional notion of SDI on its head. Instead of distributing data from a database over APIs for desktop or server-based analysis, the SDI is the database. If we build it right, any company storing their core business data in Snowflake or BigQuery, of which there's a lot, will be able to do a cloud-based spatial join to enhance their key metrics with all the data in the SDI, bringing insightful information about the world into their walls. To do this right, 2 things become really important: IDs and common data schemas. I'm Overture Maps Foundation's taking this challenge of global IDs head on, as I think it's going to be key. And the extension ecosystem of Stack can likely be adapted to define data schemas. Okay, that was a deep nerd detour, but it's a big part of why I love speaking at FOSS4G, as it's not completely insane to put this kind of stuff into a keynote. There's lots more talks that'll go deeper on this stuff, so I encourage you to check them out. And you can also learn while eating and drinking at happy hours tonight and tomorrow with the Felt crew, who added PM tile support, and the Where Robots crew, who just released their Havasu table format. Okay, so let's pull back. The idea of a cloud native spatial data infrastructure is to put all the world's spatial data on the cloud in one of a handful of formats. No APIs would be required. Each enables most all the functionality we expect of advanced servers by combining smart formatting of the data with the power of the cloud. I believe this is better in a few fundamental ways: scale, ease, and cost. One of the most important things is this architecture scales better than any server. Scalability is provided by object stores, the most scalable part of cloud infrastructures. Instead of making a custom cluster of servers, I just put it on S3. I worked with a number of people in this room on FCC's first broadband map, and we had a cluster of 3 very expensive machines running GeoServer, and it was still touch and go when it launched if this would stay up and scale. Today, you could just put that data in PM tiles and literally not worry about a thing. The S3 object store is guaranteed to scale. It's also far easier to publish data. You can drag and drop it onto a cloud console and be working with it right away. I think we as a community build tools and infrastructure to make that experience even easier, like drag and drop web UIs, QGIS plugins. But yeah, this is a great example of Copic, where you get 3D point cloud streaming as soon as the data is on the cloud. And it's far cheaper. The cloud bill for storing a terabyte of data and accessing it is $30 a month. I'm pretty sure all the vector data of most states would fit in a terabyte. Imagery is a bit bulkier, tens of terabytes, hundreds, a few $100s. I believe prioritizing the ease and cost of publishing data can fundamentally change the dynamics so SDIs become useful. Lowering the barriers to participate will enable a set of data publishers who haven't had the resource or capabilities to actually stand up servers. But I think the key will be to create compounding architectures of participation, where any data user who has interest in analysis, creates derived data, can easily participate in the SDI by simply uploading their data in the right format and filling out stack metadata, which in turn should inspire even more people to participate and publish data. My final goal for our Cloud Native SDI is that we meet users more than halfway. In particular, we aim to get spatial data in the primary tool of the financial and business world, the spreadsheet. Our goal needs to be to reduce the power of imagery and geospatial data to just a column in a spreadsheet, but a column that's powered by deep science and not obtainable in any other way. So it'll definitely be a winding road to a dynamic, successful SDI with lots of unknowns, but I want to see this community really take on the mission. I believe this community ethos of true collaboration and continual iterative improvements means we have a greater chance of really achieving the original goals of SDIs. It's going to take decades for the architecture astronauts to get things fully operational. So I think it's time we took a step up and make our goal not just building the best software for geospatial data. We need to take on the challenge of building the infrastructure and collaborations to make geospatial data truly accessible and relevant. The key, I believe, is to expand our community scope to include not just software, but standards and data. There needs to be an interplay between the three, with a focus on getting more and more useful data in cloud native formats and common data schemas. And I believe we should be ambitious, working towards global scale data sets that can be used in decision making. It's one of our big focuses at Planet, building what we call planetary variables, but we need to go far beyond what can be detected from space. And one of the biggest opportunities is open science, which is the panel this talk is kicking off. There's a real push to get more scientific data to be fully open, but publishing the data is often an afterthought and it stays in obscure formats. So I'd love to see how everyone here can work together to enable cloud native infrastructure for the open science movement, using it as a key community to collaborate with in that virtuous cycle of data, standards, and code. And we should challenge ourselves with just how easy we can make it for a scientist to drag and drop their data and have it all just work, and to show them real tangible benefits to opening their data. I'd love to see tools like Source Cooperative expand and become a repository for open science and open geospatial data the way GitHub is for source code. I think there's a ton the FOSS4G community can do to meet scientists and citizens publishing openly more than halfway. And I'm excited we convened this panel to learn more about the challenges of open science and for us to learn how we might all be able to help. I'm confident that this community has everything we need to realize the SDI vision and make the promise of Queriable Earth a reality. And I'm excited to collaborate with everyone here to do that. Thank you.